someone already told me, you will speak about density functionals. And in fact, the title is going beyond density functional approximations. But I've been working so many years with density functional, I hope I learned something from density functional, and that's the point. So the work is done with Jacek Karwowski from Torun. The last part that I consider the most interesting. So when you are, so don't go away if you are hungry, because that's how I try to keep you with the dessert. And then the middle part is Yvon, Maday, and Etienne, Polack. So I'm interested, so I don't know. Eric, you had a word, I don't know, it's a fashionable word now. What is your truth? The accepted truth, something like that. So, no, I don't know, I heard you use it. So my truth is a non-relativistic Schrödinger equation. So sorry, Maria, Eric, if he listens. So, well, so this is what I would like to, so electronic equation. And what I will speak about now is a two-step procedure. You solve the Schrödinger equation for model Hamiltonians, at least one. But you have some model Hamiltonian, and so as it's a model Hamiltonian, not the one of the system you are interested in, the results are wrong. So they're not correct results. It's a result of a model. So I need a correction, and I want to get this correction, which I correct, using exact conditions and information provided by the model system. So that's my option. And what you can take as comparison is this complete basis set calculations, where what they call complete. They make calculations with different basis sets. There are different models, but then they extrapolate in some way to what they consider the infinite basis set. With some argument, some hand waving. I try to have less hand waving than in this complete basis set argumentation. So how are the model Hamiltonians constructed? So the essential point is here to remove the singularity from the potential of interaction between electrons. So I don't work with the Coulomb interaction. So I don't try to solve the Schrödinger equation for the Coulomb interaction, but for a different interaction. And how to recover the rest? One way would be, this is an old way, so Giovanni excused himself for results that are, 15 years old. So I should excuse myself for results which are 30 years old. So it's already in several programs, but I put it as a kind of reference. Another technique is to use extrapolations. This I also already used for some years. And the last point is the really new one that is unpublished, that is about using generalized coalescence Coulomb. What happens when two electrons get close to each other? So that is the plan. So I feel a bit better after the talks given this morning by Giovanni, when he says, he had also one-dimensional systems and something like that. So I thought I would be the only one speaking about one dimension. But, so I consider two electrons. It's not needed. So for the first 2 points, it's not needed. But for the third point, I have only results in one dimension. And the system I consider is a harmonium that I will repeat shortly. Giovanni introduced it. It's a harmonium in 3 dimensions. By change of variables, you reduce the problem to one dimension. So, but this is something which is not a limitation of the methods I present, it's a limitation of my presentation. So now the plan is just what I said. So first, there will be how to remove the singularity. And then these 3 different ways to correct some errors of the model. So how to get to the Coulomb interaction from this fictitious interaction. So in this removing the singularity, the problem is how to choose it. Then I will speak about the harmonium. And how this indicates us how to add what is missing. So first choice of the modified interaction. And here is much hand-waving experience, belief, whatever. So I'm quite convinced about the need of having an operator that couples states. So you have some interaction. So in chemistry, you see lots of near degeneracy. I don't speak about degeneracy is maybe not so difficult, but near degeneracy is a headache. And you need some operators that couple states that are closer. So Francesco was talking yesterday, she had about this problem of need. There is a need of doing it. And I don't think that you can do it without, so I think it's good to have a two-electron operator there. How to choose it? You can choose a weak interaction, because it's near degenerate, a weak interaction will couple it. But you should have something there. I don't know how to get around this problem. And this is something that you can see if you put two atoms apart. You see, if there are my papers, I don't give you the reference. When I see something that interests me, I immediately try to write down the reference and the speaker goes ahead. So I put here, if you look on my list of publications, this is my publication 134, so just faster to write down. So when you look at the density matrix, we had heard a lot about density matrix, and you take two systems apart, and you have one electron in one system, and the other in the other. And they say, people try in density functional theory to speak about ensembles, and say it's the same thing like having ensembles. For the density, it is, but the first order density matrix is not. The two-body density, so if you will have exchange between A and B or not, two-body density matrix does not have this feature. You can't write it as an ensemble. So I think you need something like a way. There are phase vectors that come in. So I think you need something, a correct structure. Now there is something else when also physically and technically, short range and long range are different. So for long range, you have multipolar expansion. For short range, you can have series expansion or whatever. So you can have different techniques for the two ranges. So I think to start with, just to start thinking something, to make something useful, I thought that range separation, to have a different treatment for long range or short range, is useful. So what is, when I now have a wave function, what is useful to have is a wave function part. And I think that it's useful to have it's easier to treat the long range part because the convergence is faster in one particle basis set. So I don't need so high angular momentum in the one particle basis sets, and especially the number of determinants I generate. And to give an example for mathematicians, a few years ago, there was a mathematics chemistry workshop in Roscoff, and Boris Horomsky, presented something. I think he did it together with Hackbush. He said, he presented, I don't know why this came in here. He presented, said, okay, he wants a tensor product decomposition, and he said, okay, you use this identity. 1 over R is an integral over Gaussian, and you make a simple trapezoidal approximation, and you can express it quite well with 24 terms. So the conference was finished, I went to my hotel room, I said, how many terms do I need if I take away the singularity? In a way, it's taken away in the codes for where these density functional approximations are programmed. And it was 2-3 terms. So in order of magnitude gain in this tensor product expansion. There is also, for the short range, there is something that I physically see. So when electrons, so in the Hohenberg-Kohn theory, the idea is that the external potential doesn't matter. So you can make something for the electrons, and then you add the external potential, the potential of the nuclei. But when electrons come very close, they just see their Coulomb repulsion, and they forget about them. They see they must go away. They repel each other. And there is something I found. Maybe I should have read it, but I found in a paper about asymptotic method something which is called Darboux principle. Well, I know the paper. I have downloaded, but I have not read it. So I said, okay, well, just. And but there are so many mathematicians here. They must know what I know about. So even for asymptotic expansions, the singularities of the function matter. So the singularity is a Coulomb singularity. So if I want to correct something, I have to take care of the fact that there is a singularity that I'm missing. And this structure can be propagated. And this is the essence, in fact, of all the approximations that come. So what is, now specifically the interaction I take. So this, I use W for the interaction, not V. I like this notation because it's the two-particle interaction. And then, you see, I use the error function. And here, this is appearing in the Ewald decomposition. And this is something which shows the importance of coffee breaks. David Seppele here was at a meeting like that in Santa Barbara 20 years ago, I don't know. 95, I think it was, right? And he was in a workshop of Quantum Monte Carlo, and I was in a workshop of DFT. And there was a coffee break was common. And we start talking to the coffee break, and I tell him, you know, I'm using the Yukawa potential, but I think, don't you know something else? And he said, you know, I use the error function. And I said, just discussions, the coffee. No, I use, is there a Fourier transform? Yes, I think it. I go to the library and see the Fourier transform is a Gaussian. I say, just everything. So plane waves will work with this interaction. Gaussian codes will immediately. It's a change in a line. Oh, programs are more complicated, 5 lines to change or something like that. Immediately I did a SOSEX calculation for the electron gas, just changed my code a few lines. A few years later, Polack and George Savero Moroni did some calculation for this. It was kind of straightforward. So what are the properties of this interaction? So if you know how, another point, you see, important thing here, I have a parameter here, mu, which has nothing to do with the mu's that appear up to now. It's not a chemical potential, not a Lagrange multiplier, not a dipole moment. So it is just a parameter which defines how the interaction behaves. So look a bit at this. So if you took at r equals 0, this interaction is simply a 2 over square root pi times this parameter. So I shift the interaction first up and up and up. This is a Coulomb interaction. And this error function is something like this. Here it has a value 2 over square root. As this mu gets larger, it gets closer and closer. And asymptotically, it goes to 1 over r. That's how this behaves. And if I get this mu equals 0, I switch off the interaction. If mu becomes infinity, I have the Coulomb interaction. So I think that there are more natural ways to choose such an operator. And I don't insist, I don't speak about it, but there is a natural way to choose it, is the basis set. Once we work in a finite basis set, say we cut off our plane waves at a certain value of k, or we never see the singularity. It's something that resembles to this. So it would be more natural to use, instead of this error function, when you do a calculation of basis set, what is the operator that you are really using?
But in that case, it's not like just eliminating, you need to compensate for what you're taking away.
Exactly, that's the correction. So I do the calculation with this, or in a finite basis set, but then I have to correct. And that's a point, all the point about this is, this is my choice I make, and the second part of my talk will be about how to correct it.
So the other philosophy you could take is that you would use sort of a pseudo-potential that tries to take into account the, and then have a smaller correction. Is that?
This is kind of pseudo-potential. This is a two-particle pseudo-potential, not a one-particle like it's used in every plane wave code, but it's a two-particle pseudo-potential. And it was even called pseudo-potential. I have seen old paper where some.
But there was this old work by Prendergast and Bailly,
yes,
others,
where they said that this. They
tried to use a norm-conserving pseudo-potential.
I say it doesn't matter. It's not true. It's a convergence. But talk to any mathematician here, and they say it's a mathematical proof that the singularity gives convergence problem. There's no problem. There's no question that eliminating a singularity does not reduce.
Right. But just in terms of, do you want to, to lowest order, just sort of remove it, or just build it in?
You can try something, but then you still have to correct it. So you could do something like, and it's a question. You could do something like this, and with you can do something like this. So it's. I have nothing against it. Well, there are problems that can appear for example, if you start having oscillation and what happens in K-space, and so you can have strange phenomena. So, for example, you can have you can say I choose something no interaction at all, but then in small range you have something attractive. So you have to be. So I take something that is the most primitive way of doing it. And I think it is one of the things worth thinking about is, can this be better? And one of the reasons, because I wanted to speak later about this, one of the reasons I have some problems with this, error function is a very nice function of the real axis. But on in the complex plane, it can have a complicated structure. And I don't know if this does not make me some problems later. When I start to look more carefully in this, I'm not sure, I don't know. So I would be happy if a mathematician will have a suggestion to replace this by something else, or say, oh, it doesn't matter. Just go on with the error function. But I think that this is, and for this thing, replacing this, using this error function for correct basis sets. So you can look into this paper, but it's essentially Emmanuel Giner and Julien Toulouse who started having a series of papers and showing that just adding a density functional to this, they detect how much the basis set error is simulated by this. So the basis set description, and then they put a density functional to correct, and they have a quality like this F12 methods. It's just amazing how it works. But, well, you have the physics in there. Say, the basis set is doing this. So just correct, use the density functional correct. Okay. So the choice of the modified interaction is this. I have here a parameter. In practice, what value you take, it depends how well you can correct. You want this parameter, ideally it should be 0, so you have no non-interacting, you have something, a non-interacting system. But as I said, in practice, I'm not very convinced about it. It should at least be as small as possible. Now, let me come back to harmonium. So harmonium was already introduced by Giovanni. Okay, it's not surgical precision. So that's a Hamiltonian I'm considering. So all examples will be considered with this Hamiltonian. So there is this parameter which was also called omega by Giovanni. That's you see, it's a harmonic oscillator, and it oscillates with if you don't have the interaction. You have just a harmonic oscillator, two particles, two independent, and they interact by this error function. And, what you make a change of variables, you take the center of mass or the interelectronic distance. And the small r now on all the sides is just the distance between two parts, the vector r1 minus r2. And in general, I will need only, later you will see, I will need only the distance, the distance, I have a one-dimensional distance. So if you make this transformation, you know from the harmonic oscillator, you can transform this center of mass, like getting normal coordinates. And then the interaction appears only in the Schrödinger equation for the distance. So from 6 coordinates, I already have 3. And now you see here, the next, so you can solve the harmonic oscillator equation for the center of mass. And now you have to solve the Schrödinger equation for the distance. And you simply say it's having separates the radial from the distance from the angular part. You have the spherical harmonics. So you have an equation here for a one-dimensional Schrödinger equation that is written in the last line. This is the for this Hamiltonian, you have a Schrödinger equation. That's all. One-dimensional. So no matter what, so you can put here any interaction potential that depends on the distance. You solve it numerically, and done. But for two values, if you take omega is equal to 1/2, you can solve this equation analytically. And you know the eigenvalue is 5/4, and the eigenfunction is this one. A Gaussian times 1 plus 1/2 r, Kato-Gauss condition. That's the eigenfunction. You know the solution. That's it. You see how it behaves, the wave function behaves. And if you switch off the interaction, these terms disappear. So you have just this. And the energy is, when you go from the non-interacting system to the Coulomb interacting system, by switching on this mu, the energy is increasing monotonically.
Why doesn't it depend on mu?
Sorry? Oh, because it's this error function here. Why?
Wave function doesn't depend on mu?
Of course, here that's a wave function for mu equal infinity. And this is a wave function for mu equal 0. But in general, for arbitrary mu, it depends. Of course, it depends on mu. And I don't know if it has, and for intermediate value, I solve it numerically, or let Mathematica solve it numerically. And I get, it's a shape that you maybe, I think you can see the start of this wave function some points, but what you have is your Gaussian, and then you start, well, you will see some pictures there. So now there is a question. I think this is interesting to mention because something that is forgotten, but this is a beautiful example to see that there is something. So for example, when they construct just a function, quantum Monte Carlo, people often use anti-parallel spin and parallel spins. But in fact, what you have now a two-electron function, the part that depends on the center of mass. The wave function for the center of mass is symmetric of the interchange of particles. You are in R space, position space only. And this, you have a wave function for in the position space times a spin function. The spin function can be singlet or triplet. If you exchange spin in the singlet function, it changes sign. Triplet does not. Now the singlet function, so you look now at so we don't have any problem from the center of mass. This is always symmetric because it's you remember it depends on what was it? Center of mass was this one, R1 plus R2. You change R1 and R2, you have the same R. However, here you have a change of sign. If it has the distance times, you have distance times 1, a function of YLM, the change of sign comes from this YLM So there is no change of sign for even L. There's a change of sign for odd L. So you have this difference. So what does it matter? You can have L equals 2 and still have a singlet. And this is called by, or L equals 3 and have a triplet. And this is appeared in the paper of Kucelik and Morgan. And they call it non-natural singlet or something. They didn't speak about harmonium, but they said, well, you can. And this will affect the behavior of the wave function. If L is equal, you think it's a hydrogen atom, L is equal to 2, it's a D function, it starts with R squared. So 2 electrons are not on the same spot like for the singlets. The Jastrow factor, what we compute now, the function of R is like a Jastrow factor. The Jastrow factor is not the one that's singlet, typical singlet. So, was this disturbing? I hope so. Now we take the specific case of harmonium. So what was the choice? It was harmonium. And it was 1D, the one-dimensional radial equation. That's all I have to work with now for all the example. Now the difficult point is how to add the missing term. That was the question before. What do I have with the missing term? And this is something I learned for density functional theory. Now people in density functional theory, they say, oh, the Hohenberg-Kohn theorem. But when you look at what people do to approximate density functional, well, there are people who try to do things like that, put 1,000 parameters and say, people say something like write the functional of integral over rho to n over 3 and write sum over Cn. Okay, will I get something different? If I really make it correctly, would I get in the uniform electron gas anything different from the LDA? It's just people who develop, so you can look at the papers of Axel Becker, of John Perdue. They always think in terms of the adiabatic connection. So what's the adiabatic connection? It was also mentioned yesterday, so in this context. So I have now a lambda. This is not, again, my notation, lambda. It's just the order parameter in same perturbation theory. So I have a h, I had my h of mu. And I add the difference between h and h of mu with a parameter a lambda. So if the lambda is equal to 1, I have the normal Hamiltonian. If lambda is equal to 0, I have the Hamiltonian I wrote before. So it also satisfies Schrödinger equation and the first order perturbation theory, or Hellman-Feynman theorem, gives you that's a change in energy, the first order energy, or the change in energy is given by the wave function at lambda. So if I change lambda to lambda plus delta lambda, I need only the wave function at lambda. I don't need the wave function lambda plus delta lambda. And then if I want now to have the energy, the real energy at lambda equal 1 for the Hamiltonian here, I take that at lambda equals 0 and integrate. You see here formally, I integrate here this equation from lambda between 0 and 1. From the left-hand side, I get these two terms. From the right-hand side, I just write the integral. Okay? This is. So the correction, so this shows us that correction to my model that was this, is just this integral. That's what I need to correct. So if, say, I need to correct, I know that this is the expression. How do I do this? So if I do a density functional approximation, I take this from the, say, LDA will take this from the uniform electron gas. I try, in other correction, I have other corrections, I don't know, just try to make something. But this was, in fact, this kind of adiabatic, this appeared, apparently it's attributed to Pauli. And then a student of Pauli published something in the, I don't know, year, in the 30s. And then it came into density functional theory in the 70s. And then, so it was first Harrison Jones and Jan Langres Perdue and Gunnarsson and Lundqvist and so. And this is just a way. So hybrid functionals were introduced this way, and this is a way people who develop functionals think. So again, so the operator that is missing is the difference between the Coulomb operator and this operator here that shows up here. The difference between the Coulomb interaction and the error function up to a point. So it's a complementary error function. So if mu is sufficiently large, what this means, I don't know. It's just defined the proper way, and I don't know how. This is short range. It has a Coulomb singularity. See, this does not, but this does. And in my example, not the density functional examples, the external potential is not chosen to change. In density functional calculation, you change it. But in the techniques I will present later, I don't even change it. And everyone who knows about perturbation theory would say, never do such a stupid thing. Just, you start with a system where you have the interaction, the full interactive, you switch, you don't have a mean field, you pull away all electrons. And this, but I want to study one thing at a time, and there is so much freedom in choosing this potential that I said, I will put it apart, except when I'm doing density functional calculation. So what I have to compute is simply, you see, I replace here this error function here. I put it in the interaction, the integral I had before. And so this is a correction. This is a correction I have to calculate. Now, where lies the problem in this? I don't know this wave function. If I take here, for lambda equals 0, that's my model. But if I switch on the interaction, I don't know the wave function. That's why they take it in density functional approximation from the uniform electron gas or some models, because they say, there I know it. There are some systems where I can know it. Then what happens if I have more than just this one-dimensional system? Well, I have to perform first all the other integrals, and that complicates my presentation here, and that's why I don't do it, and because I didn't have time to. What is the essential trick with this? I don't need a change in the kinetic energy. I can use the kinetic energy of my model. See, I only use this uses only such a term which depends, which depends on the distance. When I integrate everything, depends on the distance. I don't need to take the derivative. You can do the opposite. You can get rid of the interaction, put everything in the kinetic energy or some other operator. There are many tricks that can be done. And the last point, this is directly connected to the fluctuation dissipation theorem, though I don't get into it, but I think it's generally known. So for sure. And now I come to the essential point, how to add what is missing. So the techniques, the line I follow is just, but I said here, use a adiabatic connection, but how? This is the expression I want to use, but what do I do with this wave function? I don't know. And there are three ways. First, density functionals, then extrapolations, and exact conditions. So density functionals. I'm probably late. No, how much time? Well, you have heard several times. You have this. The point is that the justification for density functions is as correct as for Kohn-Sham or something. You have this expression of Lieb, and then, but this is, people say it's a function of the density. No, it's a function of the density, but also of the interaction I have. I have to specify the interaction, otherwise I get a different functional. And that's the proof also of using Kohn-Sham. In Kohn-Sham, I eliminate the interaction and still have a density function. I have T sub s, right? So this is something which is forgotten because you look at Lipschitz, he takes evidence. I'm speaking about electrons, the interaction is Coulombic, and I continue the proof. It's not explicited, but in the proof, there this E of V depends on the interaction I put in here. And of course, the difference between if I take, so I have a universal function for each W. So I can construct like I can Kohn-Sham is just one possible choice where I choose a given W equals 0 as a reference. And here we choose another W, which depends on this mu. So as I said, in density functional theory, you want to have a potential that keeps the density constant, at least in principle, and then you change the potential also with mu. And so this complicates things a little bit, but not much. It's a ground state theory. And everything I will say when I get away from density function will not be a ground state theory. You can apply it also to excited states. Because the things I said there about perturbation theory, you can do also for excited state. You are not obliged to perturb the ground state. And what is nice in Kohn-Sham is this variational principle. That's nice. I don't have. So when I make now a density functional approximation, like in density function, I use LDA or use PB, something like that. I can make the same type of approximation, say transfer from the uniform electron gas to my system. But now it depends on the interaction mu. So I put here the mu to show that I don't use a standard LDA functional, but I use a functional that is for my, that corrects my interaction. And it was also stressed, I think Mathieu stressed it much yesterday. He said, no, the Coulomb part, you should take it out all, make it separately. So here this density function is like in what Mathieu Levin said yesterday, only exchange and correlation or correlation only, but never not put it, because otherwise you get in big trouble with DFT. And now what are the errors? As I said, when mu goes to infinity, you have here on this axis, you replace mu as a function of mu, the error made by the approximation. This delta E is and it's an atomic unit. And this curve here is the LDA approximation. So of course, at infinity, the error will be 0 by construction, because I have no correction at all. At 0, the error in LDA is larger than the error in PBE. But you see the behavior. This dotted line here represents chemical accuracy. When mu gets sufficiently large, there is practically no difference. And when you enhance this region here, this small error region with 1 kcal per mole, which is declared as chemical accuracy, see the region where this approximation works, LDA is even slightly better. So here there is something that happens. You try to correct, to make things right here. But the ways, I don't see how to correct this part. Here, LDA behaves normally, but when you get here too close, things get strange.
So what system is this for?
Always harmonium, always harmonium. No other system. So, well, of course, I have a system. I can show you this system for molecules or this. But this is a general trend that you have here a whole range where you make this change interaction, do a CI calculation with this interaction, and then correct the density functional, and then you have this. So essentially, with this basis set corrections, when they use it, they are essentially basis sets are. They take double zeta, triple zeta, and when you get to triple zeta, you essentially get already in this range, and this works.
So to get the local density approximations with the finite U, was quantum Monte Carlo done with finite U, or is that?
The calculations of uniform electron gas, you see, for obtaining LDA, it's Monte Carlo. So first it was, SOSEX, coupled clusters, say. Yeah? But then Paula made quantum Monte Carlo calculation, and this is what is used nowadays. So after around the year 2000, or I don't know when 2000, yes, late 2005 or so. quantum Monte Carlo and today. Not the same quality as, because, well, you have some release nodes, and but it's good enough. It's just, you see. So.
Sorry, what's the sensitivity of this curve with respect to the value of omega? Because I guess
omega is here always 1/2. But what happens in general, as omega gets smaller, so the regime, Giovanni would say, so, it gets better. It's just a question of scaling with distances. So omega gets smaller, things get better.
Sorry, I have another question. I'm confused because in your formalism, you have two sources of error, right? In one case, you want to correct for this replacement of the real interaction with this mu interaction, and the other source of error is the choice of the density function.
Exactly.
So which delta E is that?
It's only that, so the one-dimensional harmonium, I solve it with arbitrary accuracy. It's this one-dimensional equation. I put, I don't know, I use 10,000 points and I put 20,000 points and nothing changes. And I go out to different distances, nothing changes. So I just, to this scale here, I forget it. In fact, well, in fact, here for the LDA, I was lazy to program it in Mathematica. And I took MolPro, because MolPro is, this kind of range separation is programmed. So I didn't have to, so I put it in and just took different values of mu and then plotted. So just put there, I don't know how many basis functions. You see, there is still a small basis set error here. Yes?
Just to be clear, in your new LDA and new PBE, the only thing you are modifying is the new dependent homogeneous.
Here, no, mu LDA.
For the PBE, your enhancement factor is not modified.
No, here, so here, this is, so mu LDA is simple. You make the electron gas calculation with a change modified interaction. It's done. With PBE, it's not clear what you should do. I remember because in PBE there are RPBE, PBE Sol, and things that I remember discussing this just when I started doing this. I said, why did you do PBE something like this and so on? And I can tell you stories about this, but the chairman will not let me to tell you stories. I will tell you during lunchtime. And then, so the PBE is not a unique approximation. And so, well, you take the definition, but if you take the criteria or what you want, it's not to speak about the ansatz. So here, there might be something. So there is, for example, there is a proposal by Stoll or so. Say, I make it LDA at large for this large mu, and I make it PB here, and I have some weighting between the two, just switching on. So when I look in these things, I'm always in favor of LDA. But I wanted to avoid the question, and what does PBE do? And so I said, okay, put a plot here. Yes?
Online. So, Yvon, go ahead.
Can I ask a question?
Even two?
Yeah, go ahead.
Well, PBE is based on a model for the exchange correlation whole.
Exactly.
And therefore, given the model for the whole, one could change the interaction and deduce the corresponding energy, right?
For exchange. For the correlation, it gets more difficult because the correlation whole changes with the interaction or with lambda or this, so it's more difficult. So
okay, yeah. Okay, thanks.
Thank you. Well, thank you for the question. In fact, I thank you all for the questions. It makes me. So now the summary of density function, you can construct density functional approximation, and it's not clear what to do when the interaction is vanishing. And as there is also, in fact, I don't even think that this approximation density functions are defined for non-interacting system. I think you should at least take the limit lambda goes to 0, not lambda equals 0. but this is a different issue. Now I come to extrapolation, and I explain this, what this extrapolation is. The idea is, now I forget about density function, forget about changing the potential. I say, okay, I have here several mu's. I have several models, capital M models. So the number of M's can be, I want it small, but it can be increased. And so there is a method which was developed by Yvon, Maday and others. This is called magic points, and I don't know why they changed the name to empirical interpolation method, but for me, magic points looks much nicer. And we had to change slightly this model. But the idea is you have these several models, you have several functions. You have E of mu is a function of mu. You have it in several points of mu, and you want to see how it happens at mu equal infinity. That's what you want. And this method is a way to choose. You say, okay, I write the correction to my function. I write it in a basis set. So if I have m plus 1 points, I can determine the m plus 1 unknowns, the energy, and the coefficients. So you have, I start with 1 point, it's just my model. I put 2 points. And this method is a way to select which basis function you should take and what points is the best. It's a criterion. And so it's, you have here some basis function I used. So these colors show different basis function. And the function I want to read is this one here, this dot dashed curve. And this is something shows me already that I haven't made the good choice of a basis function, because it behaves like one in one regime, and it behaves like the other in the other regime. And switching between the two is not clear, so I don't know how to treat this problem. Open for suggestions. But you see, the basis functions are very simple here. And they are based on the asymptotic behavior. Just the leading terms as asymptotic behavior. And now you see how catastrophic this model is. So the model gives you this black curve here. The domain of chemical accuracy is these things that you can't see here on the axis, and the previous curve, LDA, and over here. Half an atomic unit of, you imagine what it is, half an atomic unit of at the origin, it's just you increase it, and at mu equal 3, you can see this here. You start approaching chemical accuracy model. It's far off. But so let us take this wave function and compute the expectation value of the Hamiltonian with this wave function. Well, you get this gray curve here. It's not so bad, but LDA is better. Increase the scale, this curve. Well, you see here it's even better. Just not there's some. But now you start adding points and basis functions. It's here, the previous plot was cut here, so it's a bit larger. So we see the model, something, 2 points, 3 points. See the first, by this scheme, they are flat. They cover more or less the same region as the density function, but their function gets flat. I catch the right behavior. But here, there's a point, you get further and further, seem to get further, but there are some, it gets more and more difficult as you get at small values of mu. So it works, but needs a few points, and has this wall at small mu. And now I come to the point where I need 1 point. I just have one model and correct it. And this is based, there are many papers, and you can find references to this paper in this review paper. In fact, where they present the methods that is presented in 2 other papers. And I think it is a paper who has not received as much attention, or as much attention as they needed. The idea, this is something which is not related to two particles, but you see it immediately, you can see it also for the hydrogen atom. When you look at the Hamiltonian operator, and you say calculate h psi over psi, is a constant, is energy, is eigenvalue. So but you see here, for example, you multiply psi this term, you have a divergence. On the left-hand side, you would have a divergence. So h psi, well, so what's happening there? The wave function must have a special structure in order not to produce a divergence. So put it in and see how the wave function, what the behavior of the wave function is. And this term that looks divergence means that the wave function has to start with r to the power L. That was what I said before about d function and so on. No? And so you try to expand it this way. There was a paper by Fournet and Hoffmann-Hostenhoff and so on. I think I asked Heinz-Jürgen Flatt what he thinks. So if I'm right about this, you say, oh, there is this paper. I think you are right. And in fact, there is something in the abstract of the paper. Say, you can do something like that. So if you are away from other singularities, if you put two electrons close to each other, but not on another singularity, you can do things like. But he didn't want to work on this. I hoped he would. So what I'm saying here is not that this is an exact condition of the wave function, but this is a condition I want to impose on the test function. I take a test function of this form, and I want to eliminate in the test function the singularities. And then how do I do it? I take here powers. Okay. So you get some equations, of which the first is a Kato-Kas condition, and then you get other conditions. You don't eliminate this C0, you have the dependence on the energy. And at a certain point of the external potential. The external potential, the potential, you also expand it. And you have some equations, and I thought I will be able to finish. There are 2 points here. I should have, it's 50 minutes over.
Right, but we have some time for questions.
Okay. No, there are two tricks to do here. You can look asymptotic, what happens? Okay, I was sure I will miss the most important part. So there is a trick here, how to do when mu goes to infinity, to see how the wave function behaves. And the behavior in the origin brings you an explicit mu and lambda dependence and a constant, a prefactor, which in fact is related, it's related to what people call the on-top pair density, which is a very important ingredient in density function approximation when you square this. And it's this unknown prefactor. As you have eliminated the lambda and mu dependence, you can, and you have now, you use expansion I was speaking before, and you can compute everything almost, it's analytically. And so, in fact, you get an expression like this. You need to have these expectation values for the model distance, and then you have an integral, which is an integral, this is this integral here. Can you see it? It's an integral over R, and here you have a mu and lambda dependence, and these coefficients that are mu and lambda dependent. And you have this, you have eliminated the mu and lambda. Okay, are dependent on each other, and it's okay. And well, you have to calculate this, and this shows you how the wave function behaves in small r, at small r. Small, you see the distance goes here to 2 atomic units in the plot. And you see here that's a non-interacting system, so you have no cusp condition. You have this type of interaction. You don't have a cusp. And then, but if with lambda you switch on the cusp. But as you take the expansion larger and larger, you get a short range You start to follow it. And this is something that is interesting, I think. That's a wave function for harmonium with the exact Coulomb interact with a black curve, this curve here. You take this expansion to order r to the 7, and you get this curve. Of course, it diverges after a certain point. You eliminate the external potential, so you may have a free particle with the same energy, and you have a solution, which is this red curve. So at short range, even changing the potential does not affect it much. So it's something you see from density functional theory. And you see, in fact, this potential appears only in higher order. Well, I just to show you, you see, if the wave function is followed, and I explore it with a short-range potential, then, of course, results will be right up to a point, and there, again, I get to this. So I don't show, there are many curves like this, all similar. So I say, maybe one thing to, you see, when I take all these curves here, this is the expectation value of the Hamiltonian. None of these curves uses more information provided by the model than the expectation value of the Hamiltonian. And they all get better. And so it's better than Kato-Kasper. I put just the last slide, just to overview. So what is missing here? In DFT, we have a local treatment. Here it's a global treatment. Here, I said the model interaction might be changed. So this basis set extrapolation is satisfactory, but for me, it's not clear how to improve the basis set. The basis here, when I did the short-range expansion, I took powers of R. But maybe there is something like this cumulant type of thing. Maybe it's possible to correct it, to make it, not to have these divergences. And mathematically, it's founded for a chemist, but not for a mathematician. And we have this small, this wall, and the question is, can we eliminate it or not? I think it's not clear to me if it can be eliminated, something can be done or not. Okay, thank you.